basic differential equations. What's a basic kind of differential equation? It's an equation, so there's an equal sign, involving a derivative. Differential dy and dx individually are sometimes called differentials. Actually, I call them infinitesimals. Both names are applicable. Differential equation. The simplest kinds of differential equations are those that can be found by direct integration. And let me pick kind of a strange function here. Let me pick the arctangent function, which of course, again, is the same as the inverse tangent function. I'm writing it both ways, but in any homework problem or exam problem, you'd probably only see it one way. I'm after a function whose derivative is always the arctangent function. Don't say it too quickly. The answer is not 1 over 1 plus x squared. The derivative of arctangent is 1 over 1 plus x squared. In other words, the integral of 1 over 1 plus x squared is the arctangent function plus c, but that's not what we're doing here. We're not integrating 1 over 1 plus x squared. We're integrating arctangent. We are after the most general solution of this, the most general function whose derivative is always the arctangent function. We got to integrate arctangent. The so-called general solution, that's an abbreviation for general solution, is just the integral of the arctangent function, not the integral of 1 over 1 plus x squared. And the answer to this integral is not 1 over 1 plus x squared, because that would be the derivative of the arctangent function, not the integral. So what do? It's integration by parts. It's similar to those problems from last Friday involving the natural log function. Write the function we're trying to integrate as a product. Since it's just one function, the other factor, it has to be 1. Decide what u and v prime should be, keeping in mind the most important piece of advice in deciding is that v prime should be something easy to integrate to find v. You want to be chosen so u prime is often simpler, but more importantly, v prime needs to be something easy to integrate. So I would not want this to be 1 and this to be arctangent, because then to find v, I'd be doing the exact same problem I'm trying to do in the first place. So try the other way around. Pick this to be the arctangent function and this to be 1. Then v is certainly easy to find. Just integrate 1 to get x. No plus c necessary. U prime is not too hard to find either. It's not a super simple function, but at least it doesn't involve a trig function or an inverse trig function. So in that sense, it's simpler. Now apply integration by parts. When you're first learning this, it's almost always best, and also on your homework for the sake of showing work, to write down the general formula, uv minus the integral of v times u prime with respect to x. Everything is a function of x. If you set up your u, v prime, u prime, and v in this table here, u times v is the product of the functions on the main diagonal from upper left to lower right. And v times u prime is the product of the number of the functions at the bottom here. So this becomes u times v is x times arctangent of x minus the integral of v times u prime. The product of these two things is x over 1 plus x squared. You're always hoping that when you apply integration by parts, you get a new integral that's easier to do. Is this easier to do? It doesn't look super simple. It is easier. In fact, it could be done by guessing if you're experienced enough. But I think this is Most of you are not experienced enough to know how to guess here. Do notice if I let w equal 1 plus x squared, then dw is almost in the numerator. dw would be 2x dx. We have an x dx there instead of a 2x dx. Well, we're close. Just divide both sides by 2. 1/2 dw is x dx. So we get, don't forget the first part. If you forget that, it's wrong. X arctangent of x minus, in terms of w, it's going to be 1/2 in front of the integral, 1 over w dw. So we get x arctangent of x minus 1/2 natural log of the absolute value of w plus c. Not done, because we don't want any w's in the final answer. So we need to use this substitution now to help us simplify in terms of x. And notice that 1 plus x squared is always positive. Therefore, I can get rid of the absolute value signs. The final answer is x arctangent of x minus 1/2 ln of 1 plus x squared plus c. The 1/2 by property of exponents of logarithms, could also be brought up into the exponent of 1 plus x squared. So you could have a ln of square root of 1 plus x squared, but this is good enough. Note again, 1 plus x squared is always greater than or equal to 1, which is positive. So I don't need the absolute value signs. We're not plugging in imaginary numbers for x if you're worried about that. So this is okay. Look at that answer. It would probably be something you would never guess, or at least it would take a long time to guess it. So integration by parts plus substitution gets us the right answer. I'm not going to take the time to check it, but if we did, we would need the product rule. We would ultimately need to do some simplification before we ultimately got arctangent of x. But if you do it right, it should work. That's a general solution of the differential equation again. Remember, that's the context here. Where c is arbitrary, it represents infinitely many functions that all solve the differential equation, that all have a derivative equal to the arctangent of x. But with differential equations, usually you also have an initial condition, some starting value, like if it's a starting height or a starting velocity, for example. Let's go back up to the differential equation and let's add an initial condition. Y of 0 equals something. Here we are abusing notation. It's okay. This is a case where we're okay with it. Y of 0 equals some number. I'll pick 1. Then these two equations together make up something called an IVP, which stands for initial value problem. Whereas the differential equation by itself has infinitely many answers, because C can be anything. The initial value problem has just one answer. A unique solution of the initial value problem. We've got to figure out what C is. 1 equals y of 0, replace x with 0. What do we get? This is 0. This is 0, right? ln of 1 is 0. We just get C. C must be 1, the initial value. Therefore, unique solution of the initial value problem is just one function, y equals x arctan x minus 1/2 ln of 1 plus x squared plus 1. Infinitely many solutions of the differential equation, but if I add the initial condition, I get a unique solution. Typically, most differential equations have infinitely many solutions, and typically most initial value problems have one solution. There are some weird initial value problems that have more than one solution, But we mostly try to avoid those because that's weird. Because like, what would that model in real life? It would model predicting two different things. I mean, maybe that could happen in quantum mechanics or something, but from most real life models, you don't want more than one solution when you know the initial condition. We'll end class by doing a second example, a little quicker. The differential equations are in section 6.3. Most of the examples in that section are easier than what we're doing here. And if you look at the mini exam from 2016, I believe if I have a problem like that on here, it's an easier one. But we're also trying to practice integration by parts. Let's do a similar example, now arcsine instead of arctangent, also called inverse sine. Once again, it's a fairly basic differential equation. We're after a function whose derivative is always arcsine. So do the integral of arcsine. There are some differential equations that are more complicated, where the right-hand side maybe involves y as well, weirdly. And then just a basic integration doesn't work. But here we're trying to find a function, the most general function whose derivative is arcsine of x. Once again, imagine a 1 in front of there. Use integration by parts again. And just like before, let v prime be the 1 and u be the arcsine. Before it was arctangent. V is easy to find. U prime is, well, is this simpler or not? It depends on your definition of simpler. It doesn't involve any trig functions or inverse trig functions anymore, but it does involve a square root now. It's okay, it can be done. Write down the integration by parts formula. Get it in your head by writing it down every time. Do u times v, x times arcsine x, minus the integral of v times u prime will be minus the integral of x over square root of 1 minus x squared. Our original integral is replaced with something minus a new integral that we hope is easier to do. By the way, sometimes the integrals aren't easier to do. Sometimes they're the same level of difficulty. Sometimes they could be harder. If they're harder, that means you better back up and try again. If they're the same level of difficulty, a trick might be useful. And this does come up in your homework. I'm not going to have time to talk about the trick, but I will refer you to a video that I made where I do the trick. I think maybe there's an example in the book too, where you have to solve algebraically ultimately for your integral. It's a little weird, but I'll refer you to that. But how do you do this integral? Doesn't look very easy until you realize if I let w be 1 minus x squared, then dw is almost in the top there. dw is negative 2x dx. In other words, negative 1/2 dw is x dx. You see the x dx here. This is set up to work nicely. So now, don't forget the first part. I get x arcsine x. Okay, careful, this is tricky. I've got two minus signs making a plus sign. I also have a 1/2, so I get a plus 1/2 integral of what? Replace the 1 minus x squared with w, so I get 1 over square root of w. Same as w to the negative 1/2. Again, the two minus signs make a plus. The 1/2 can come out in front. What's left in the integral is 1 over square root of w dw. But 1 over square root of w is the same as w to the negative 1/2. This is good because that integral is now relatively easy to do. Add 1 to the exponent, divide by that same number, plus c. These 1/2s cancel. Right, dividing by a half like that is the same as multiplying the whole thing by 2. Replace W with 1 minus x squared, and write that as the square root. So if I have not made a mistake, there's your most general antiderivative of the arcsine function. You could check it. It would involve product rule and some simplification. What about the initial condition? Same as the initial condition as the previous example, y of 0 equals 1. Does that mean the c will equal 1? No, in fact, in this case, it doesn't. C is not always the initial value. Yes, this thing is 0, but this thing is a 1. This simplifies to 1 plus c. Solve for c, subtract 1 from both sides. That means c is 0, even though the initial value is 1. Your unique solution of the initial value problem is x arcsine of x plus square root of 1 minus x squared plus 0, which I won't bother writing. This is general solution. This is one unique solution to the initial value problem. General solution of differential equation, unique solution of initial value problem. Again, the problems in section 6.3 are easier than this because you don't have to do integration by parts for one thing. But you should know the idea of what we're doing.